Hello, welcome back to this video series on cryptography. In this segment, I'm going to talk about the Rabin encryption system. In particular, I will be talking about chosen ciphertext attack on Rabin encryption system. Let me briefly summarize what the Rabin encryption system is. The plain encryption system works as follows. Suppose you have a message M you would like to send. Say Alice is here, Bob is here. Alice wants to send to Bob a message M. What Alice will do is she will compute. Let me use the letter X to denote the message. Okay, so this is what Alice will compute. X is the message she wants to send to Bob. Alice will use Bob's public key. Bob will publish N. Some books use capital N, some books use small n. I'm just using small n in this case. N is the public key made of two primes P and Q. P and Q are a secret Bob only knows. The assumption is that given n, it is difficult to find P and Q. That's the assumption. So all Alice does is she takes her X, the message X, computes the square of it, computes the mod n, and sends the value Y to Bob. Okay, this is the Alice's encryption part. Let me call this as the encryption, right? Performed by Alice. How about decryption? Decryption is now the process performed by Bob. He takes the Y and he inverts. So informally speaking, he does root Y mod n. There is an interesting problem here. Why can't an attacker do the root Y, right? If he or she can do root Y, then he can also get X, right? But that is also another interesting problem. We don't know how to compute square root in a modular arithmetic context. So there are two problems here. We don't know how to factor large numbers. We don't know how to compute the square root in modular arithmetic for large primes. If your number n, the public key, is made of say 2048 bit, then it's difficult to factor such an n. That's basically the computational hardness problem assumed throughout in cryptography in many places. Okay, so only if you know P and Q, then you can easily compute the square root of Y. We learned in the other segment that there are multiple solutions actually. When Bob decrypts, Bob will not be sure exactly the X that Alice sent. Bob can actually get 4 different solutions. So informally speaking, Bob will not know whether it was X1 or X2 or X3, X4. It could be any of these messages, 3 messages that will, if you square any of these, you may still get a Y. Okay, Y is the value Alice sent, right? X is the message. So how will Bob know which X to pick? Unless there is some redundancy in the message, like a message has some kind of a header saying a message equal to or something like that, there's no way for Bob to know that, right? I have talked about this in my other segments, so please watch that. Okay, now what is the problem I'm going to talk about today is given Y, can we find X using an oracle? Okay, an oracle is a chosen ciphertext oracle in this context. Okay, so let me clarify what I mean by that. So when Alice is sending a message to Bob, right, she sends the ciphertext Y to Bob, right? What if the attacker is allowed to have an oracle? Of course, the goal of the attacker is to learn X, right? This is the goal. Okay. What if we allow the attacker to interact with, let's say, attacker Eve is here, right? She is allowed to interact with Bob. Okay, this is so Y. See, let's say Bob is, let's say Eve is allowed to send whatever values she likes. Z, let's say Z is some other value, and Bob will reply back to Eve with an encryption. Let's say Bob replies with a decryption of Z. Okay, it's an interesting scenario now. So you have an oracle here. Let me be clear what the oracle is. The oracle takes as an input some ciphertext. Okay, say Z is some ciphertext. It will give decryption of Z as a reply back to Eve Okay, this is called the chosen ciphertext attack because the attacker Eve is submitting ciphertext. Z is the ciphertext. Okay, what is the reply she's getting back from Bob? Plain text, the decryption of Z. Okay, you may wonder how can this help Eve to learn X? The answer is pretty neat. Because of the way the mathematics works here. Let me now dive into the math part. Okay, so let's talk about the algorithm now. And the algorithm part is like this. Suppose Eve, here is Eve. Eve randomly picks an element R, right? And computes, say, y equal to R square mod m or mod n, right? Mod n. N is the public key of Bob. Eve can compute this easily, right? N is public, R is a random number she picked, and she will now submit this Y to Oracle and ask the Oracle, please decrypt this for me. Okay, Oracle is the chosen ciphertext attack scenario. You may think that there is no benefit of this because Oracle of Y is going to give back R, right? But that's not always the case. The reason is that, remember, there are 4 possible routes. So the Oracle may reply sometimes R, sometimes R. Let's say this corresponds to R for a moment. Okay, sometimes it may return R, sometimes it may return minus R, sometimes it may return some other number. We don't know, whatever, x3, x4. Okay, so there are 4 possibilities. The interesting scenario is that what happens if Oracle replies a Y. So okay, let me explain clearly. Oracle is taking as an input Y, right, ciphertext, and it's going to reply with some X, right? What happens if that X is different from, that X is not the same as R or minus R? Okay, that's going to be interesting now. So you got an X, when you square it, okay, let me explain this. So you got an X from the Oracle. When you square it, you get R square, right? Because you sent an encryption of R, it's going to give you back one of the 4 roots, okay, of Y. The problem now is what happens, the reply you get back is not same as R or minus R. Okay, let's say that scenario is true. In that case, what happens now is the following. We have a scenario where your X is different from R and minus R. All the work Eve has to do is this. Let me explain the reasoning behind it. One moment. Eve has to compute GCD of these 2 things. It will be one of the factors, say P. Okay, which is a secret. Remember, P is a secret. Let's think about why would GCD of X plus R comma N is going to be P. Okay, the reasoning is as follows. Remember, from a Chinese remainder theorem perspective, we can use Chinese remainder theorem to reason about it. There are multiple ways we can reason about it, but I'm going to use the Chinese remainder theorem. Okay, so all I'm going to do is, let me show you the Chinese remainder. We talked about Chinese remainder theorem in the other segment. So I encourage you to watch that first. Okay. So let's take this X. Okay. If you have a point X in say Zn star, from Chinese remainder theorem, we learned that we can project this point into 2 other points. XP, that means X mod P and X mod Q. Okay. So, which means if you take this equation y equal to x square mod n for a moment, xp xq square gives you y, right? That's the meaning of the statement. So because of the properties of power of 2, we can also say minus xp comma xq should also be one of the square roots of y, because it's minus outside, right? You can just square it, minus will disappear. So another possibility is xp minus xq. Another possibility is xp minus xp minus xq. Okay, so these are the possible square roots, the 4 square roots of y, right? These are the only 4 possible square roots. Okay, that's why I said there are 4 square roots here. Okay, now let's pay attention to all of these 4 possible square roots. Okay, now what can we say about this one? Let's say this is x, right? This is x. What can we say about this? This becomes minus x because the components are reversed by multiplying by minus 1. Okay, so we have x and minus x. Okay, so what is left is this one and this one. Okay, these are the 2 components we are left with. Okay, let's call this to be r for a moment. Okay, when we map this back to z and star, we get an r. Okay, now let's think about what is the meaning of a x plus r. Okay, this is x and this is r, I said. X plus r is now simple. X plus r is nothing but, we map it to 0, 2 x q. You have to do mod p, mod q, sorry, mod q. I'll use percentage q to denote mod q. Okay. Okay, this is interesting now. This is 2xq, just to be clear, because I'm adding the component by component. Okay, I'm using Chinese remainder theorem to map this. What does this tell us? This tells us that the first component is 0, which means x plus r. Okay, let me do this way, which means let me clarify a bit here, which means x plus r mod p, right, is 0, which means p perfectly divides x plus r. Okay, that's really interesting. So when you have a p which divides x plus r, we know that p is part of n. Therefore, GCD of x plus r comma n is p. That's the reasoning behind the attempt made by Eve to figure out the prime factors of n. Okay, I have mixed up small and capital N. Please forgive me, it's the same. Yeah, I will put small n here. Okay, so x plus r shares some factors with p. It could be 2p, 3p, who knows, some multiples of p. Therefore, by definition of GCD, if you take GCD of x plus r with the n, you will get a p. And that's all. This is the basic idea of how we can perform chosen ciphertext attack. In cryptography, we call it CCA, chosen ciphertext attack. And what I have done is basically allow Eve to submit whatever ciphertext she likes to Bob. Bob has an oracle, it will reply back with a decryption. And because of the way the mathematical structure of this group works, there are 4 possible routes. The problem is that one of the routes, if we get one of the roots that is different from r or minus r, in this case y equal to r square mod n for a random r, we can easily factor it. Okay, what is the probability that this can happen? Meaning you choose an r as a Eve, you do r square mod n, and then you submit your y and ask for the oracle of y. If oracle of y comes back with r or minus r, bad luck, throw away that r, generate a new r, and continue until this is successful. Okay, But look at the space of possible values. There are 4 possible square roots. 2 of them are bad, 2 of them are good, meaning r and minus r are useless for us because they will not be helpful for us to solve this problem. So we have only 2 other roots that are of interest for us. That means the probability of success is 2 over 4 or half, which is really nice. That means for every 2 attempts, you will have 1 success, which is really good. If you take an R, you submit it for decryption, y square or y equal to r square mod n. If you don't get r or minus r, you stop. Otherwise, you continue with generating a new R. That's basically the approach for cracking the Rabin encryption system using chosen ciphertext attack. And this could be arguably one of the reasons why Rabin system is not really used in practice. Although it's remarkable that breaking Rabin is same as factoring, right? Because we already factored the number n and find the primes p and q, which is not the case in RSA. RSA doesn't provide this mathematical equivalence between factoring and breaking RSA. However, you can perform chosen ciphertext attack also in raw RSA, which I have talked about in other segments. But you may not be able to break or find the factors of n in that context. Here you can find the factors of n right away. So let me summarize what I talked about before going to the demo. From Eve's perspective, E randomly picks an R, submits encryption of that, meaning R square mod n to Bob. Bob as an oracle, it will reply back with the decryption. And if the decryption returns value x different from R or minus R, right? Not R, you don't want R or minus R as a reply. Then you have 2 other roots, okay? Those 2 roots can be helpful for you to figure out the prime factors, okay, of n. So you can pick one of the roots that you get back. The decryption oracle will give you back one of the roots. All you have to do is take the x that you get back from the oracle and add it to your R and do a GCD of x plus r comma n. GCD is a polynomial, is easy to compute, very easy. And x plus r, x is reply coming from Bob, so Eve knows that. R is something that Eve choose. N is public, so all of these components are publicly available, and you get the private component n. Okay, that's all. That's the only thing I did. Okay, and it's nice that I can use Chinese reminder theorem to prove that why GCD of x plus r comma n gives you p. Okay, let's do a quick demo now. Okay, the demo is going to help you to understand how we can do this attack in real work. Okay, so as I said earlier in the demo, on my whiteboard there is a decryption oracle which takes a ciphertext as an input and it gives back decryption of that ciphertext. Okay, and the rest are all the standard Rabin encryption scheme. This is a plain encryption scheme, right? You take a message, you square it, take mod n, that gives you the encryption. A decryption is basically finding the square roots and giving you 4 square roots, right? But the decryption oracle will pick one of the square roots and send it to the attacker Eve. All Eve has to do is do this little loop here. Randomly picks an R, computes the encryption of it, submits to the random oracle, or decryption oracle, not random oracles, decryption oracle, and counts. In this case, I'm counting how many attempts needed. Anyway, as I mentioned on the whiteboard, our x has to be different from R as well as from minus R. That's the reason why I wrote it in programming like this. And then all you have to do is compute the GCD of x plus R and n, and get the prime factors p and q. Okay, that's all. So let me run it for you and show it to you. So the question is, can you factor n? It's going to print an n and ask Eve to factor it. With an oracle, Eve will be able to factor it. Okay, it's going to take some time. Maybe I should stop this and run with 1024. One possibility. But let's see. Maybe it comes quick. If not, we can run it with 1024. So it's generating a 2048-bit a number first, which takes a few milliseconds on a remote machine. Then it's going to factor the prime numbers hidden inside the number n. Okay, oh, here it is. Here it is. So the challenge starts by this, right? It says, can you factor n? Maybe I should run it again with a smaller number just to get the idea across first. Okay, I'm running a, yeah, it's easy. So challenge is this: you're given a number n to factor, right? And it's asking, can you factor n? And the attacker Eve is doing this portion of the computing, right? Generates a random number R, encrypts it, submits to the decryption oracle, checks whether the reply X she gets back from the decryption oracle is different from R or minus R, right? That's basically what it means. If yes, computes X plus R GCD with the n, finds the first factor P, second factor Q, multiply to assert, and you can see here only 7 atoms are needed in this case, meaning 7 different random numbers were needed. But if I increase the size of the key, maybe it's very easy. Let's try that. Yeah, you see here only 2 atoms are needed to get back the prime factors, meaning only 2 different random numbers or were selected. Here I have a loop, right? I need only 2 of those random numbers to find this. I actually tried it with even 2048, and let's see what happens now. It's going to take some time because it's trying hard to break this large number. Yeah, it took 4 attempts. Only 4 different random numbers were needed to break this 2048 number and find its prime factors. Okay, so what is the reason this was possible? The reason this was possible is the following, right? Eve generated different random numbers, or takes each random number, computes the encryption, submits the chosen ciphertext to the decryptor Bob. Eve knows the number that she picked, right? If the response is different from R or minus R, she knows that all she has to do is computing the GCD of X plus R with n. X is the reply she got back from the decryption oracle. And this line is extremely simple, GCD of X plus R n, and she gets the prime factor P. Okay, and the other factor is n by P. Okay, so the main message is as follows. A Rabin encryption system is a very novel idea, okay? All you have to do is take your X, compute X square mod n. For encryption, decryption is just square root of Y. And then among the 4 possible roots, you pick the root that has some redundancy, meaning some indication that this is a message. Otherwise, there are 4 messages. Okay, that's a great idea. However, the problem is that the decryption oracle, okay, is a problem. Meaning, if you submit arbitrary chosen ciphertext and you get back its decryption, you can use that to break the system completely and find the prime factors. That's one of the main reasons I believe Rabin is not actively used in the field. But one novel idea is that breaking RSA is not necessarily equal to breaking the prime factors or finding the prime factors. But in the Rabin case, we have just discussed, breaking Rabin is equivalent to finding the prime factors. Okay, because if you know how to find the square roots, if you know how to find a square root of a given number in Z and star, you know how to find the prime factors. I just shown you the algorithm here, this portion of the discussion here. All right, that's basically what I wanted to show to you. Thank you very much for your attention.